Welcome to This Explainer. Today, we're diving right into a seriously fascinating journey. We're going to trace the path of just a single ray of light to uncover the fundamental rules of optics, the very rules that govern how we see the universe. It's a journey that reveals how something as everyday as your reflection in a bathroom mirror or as complex as the brilliant sparkle of a diamond literally all comes down to a few really elegant laws of physics. So, let's jump in.
First things first, we need to understand our light source. And the contrast here is pretty wild. You see, an everyday light bulb is kind of messy. It scatters energy everywhere, in all directions. But physicists, well, they often use a laser. A laser produces a super narrow beam of monochromatic light, which just means it's all a single color or wavelength. Because all of that energy is concentrated into one intense, narrow path rather than spreading out, it lets us clearly trace its exact journey. Oh, and as a quick aside, it's also exactly why you must always protect your eyes and never look directly into a laser pointer. That concentrated energy is no joke. It can easily scar your retina.
To demystify light's complex behaviors, we're going to explore 5 key phenomena today: the law of reflection, refraction, total internal reflection, lenses and the eye, and we'll wrap up with dispersion.
Okay, Section 1, the law of reflection. Let's start with the absolute simplest interaction: light bouncing off a shiny surface.
When an incoming ray of light, which we call the incident ray, hits a flat mirror, it bounces off at the exact same angle it arrived. But here's the trick, and it's absolutely crucial. Physicists always measure these angles relative to an imaginary perpendicular line drawn at exactly 90 degrees to the surface. We call this line the normal. So the angle of incidence, I, is always equal to the angle of reflection, R. Honestly, it's exactly like throwing a bouncy ball perfectly against a perfectly smooth wall.
Now, this predictable bouncing creates a really fascinating real-world effect. It leads us to a classic observation. Have you ever noticed that emergency vehicles write their names completely backwards on the front of the truck? Why on earth do they do that?
Well, this brilliantly illustrates our first optical phenomenon, lateral inversion. Because flat plane mirrors reflect rays at equal angles, they create images where left and right are completely reversed. So when a driver is looking in their flat rearview mirror, that backwards text on the front of the ambulance is reversed again, making the word perfectly readable in a split-second emergency. Pretty clever, right?
But here's where it gets kind of trippy. The image you see in that mirror isn't actually there at all. We classify it as a virtual image. See, a real image is one that can actually be projected onto a physical screen. But a virtual image? Nope. In reality, no actual light rays are coming from behind the mirror. Your brain simply gets tricked. It assumes that the light rays reflecting into your eyes traveled in a straight line, which creates the illusion of an image just hovering there behind the glass.
So, to prove exactly where this virtual image forms, physicists don't just guess. We use systematic ray diagrams. It's like a giant puzzle. You draw the object, send 2 incident rays toward the mirror, bounce them off at equal angles from that normal line we talked about, and then, here's the secret, you extend those reflected rays backward with dashed lines to find exactly where they intersect. When you complete the diagram, you can see how the dashed lines perfectly intersect behind the mirror. The resulting virtual image is completely upright, the exact same size as the original object, and sits the exact same distance behind the mirror as the object is in front of it. It's a perfect, symmetrical illusion.
Moving on to Section 2, refraction. What happens when light doesn't bounce off a surface, but actually passes right through the boundary into a totally new medium, like water?
Well, when light travels from one medium to another, it actually changes speed. And if it hits that new boundary at an angle, that sudden change in speed causes a change in direction. This bending of light is called refraction. It is the exact reason why, if you look at a straight straw sitting in a glass of water, it appears completely snapped or bent right at the surface. You've definitely seen this before.
But this bending isn't just random. It's strictly governed by a mathematical value known as the material's refractive index, represented by a little n. Basically, the higher the refractive index, the more the material hits the brakes and slows down the light. When light passes from air into a denser medium like glass, it slows down and bends towards the normal line. And when it travels out of that glass back into the open air, it speeds up and bends away from the normal.
Which brings us to Section 3, the critical angle and TIR. Because that simple act of bending away from the normal leads to one of the most powerful phenomena in all of optics. So imagine this. If you keep increasing the angle at which light tries to exit the glass, eventually it's going to refract at exactly 90 degrees, just skimming perfectly along the surface. We call this specific incident angle the critical angle.
Now, if you increase the angle of incidence even slightly past that critical angle, no way, the light doesn't exit at all. It undergoes total internal reflection. Literally, 100% of the light is reflected back inside the material, turning the inside of clear glass into a perfect mirror.
And we can actually calculate this exact trapping point. Let's take a diamond, for example. Diamonds have an incredibly high refractive index of 2.40. If we use the equation sin C equals 1 over n, we find the critical angle is incredibly small, just 24.6 degrees. Because this threshold is so tiny, nearly all the light that enters a diamond hits the inside facets at an angle greater than 24.6 degrees. So it gets totally internally reflected, just bouncing around endlessly inside before finally escaping. That is exactly what gives diamonds their famous, brilliant sparkle.
But, total internal reflection isn't just for making jewelry look pretty. It's an absolute game changer for technology. It's the foundational physics behind optical fibers. By trapping light inside a thin, flexible glass core, we can literally bounce data across the globe at the speed of light for the internet. And in medicine, doctors use bundles of these fibers in endoscopes, allowing them to snake a cable down into a patient's stomach and look around brightly, without needing to do any major surgery at all.
All right, section 4, lenses and the eye. Let's look at how we can purposefully shape glass to bend light and actually correct our own biological machinery.
So our eyes naturally use a flexible, convex lens to form images on the retina. But let's be real, sometimes it isn't perfectly calibrated. If someone is short-sighted, their eye's lens is actually a bit too powerful, focusing the image too early. To fix this, we put a diverging lens in front of the eye, which just slightly spreads the light rays out before they even enter. On the flip side, if someone is long-sighted, their lens is too weak. We fix that using a converging lens, which helps bend those parallel rays together so they meet exactly at the correct focal point on the back of the eye. It's physics coming to the rescue.
Finally, section 5, dispersion. For our last stop along the ray's journey, we're going to see what happens when extreme refraction splits light apart entirely.
When ordinary white light passes through a triangular glass prism, it refracts and separates out into a completely beautiful spectrum. But if we grab that red laser from the very beginning and pass it through the exact same prism, it bends, sure, but it stays a single, solid beam.
This contrast right here brilliantly proves the true nature of white light. White light isn't just one color. It is a rich, packed mixture of all the different wavelengths of the visible spectrum. Dispersion happens because each separate color gets refracted by a slightly different amount when it hits the glass. But a monochromatic laser, it's already just one single wavelength, so there's literally nothing in there to split apart.
Sir Isaac Newton actually proved this way back in the 17th century. As the white light enters the prism, all the colors slow down, but they don't slow down equally. Violet light hits the brakes the hardest, slowing down the most, which means its direction changes the most, bending it right to the bottom of the spectrum. Red light, on the other hand, slows down the least, so it's refracted the least, cruising along at the top. This unequal bending is what reveals the famous 7 colors: red, orange, yellow, green, blue, indigo, and violet. So as we wrap up this journey today, we come right back to the central, elegant truth. Everything we've talked about, from the backwards ambulance text, to the sparkle of a diamond, to the rainbow coming out of a prism, fundamentally stems from this one simple rule about light changing its speed and direction when it hits a new surface.
Before we go, I want you to try something. Look around the room you're sitting in right now. Are you looking through glasses that are actively refracting light to correct your vision? Are you seeing a virtual image reflected in a window? Which of these fundamental rules of optics is shaping your reality at this exact second? Keep observing, keep asking questions, and I'll see you in the next explainer.